Here we are, everybody. We're in part 3 of this mammoth task of working through the problems that will lead you to success in the GCSE Higher paper. And we're kicking off with some 3D trig. If you haven't seen part 1 and 2, they cover really good basics. But trig, it's kind of separate apart from the end of the previous video where we're going to look through it like 2D. It's best to do 2D trig before you do 3D trig. Okay, let's get started. In the roof of a shed, see below, find the length BC and angle BFC. Okay, so remember we're looking for some spatial awareness here to identify a triangle we can work with. We sometimes don't always know where to start. Maybe we can't jump straight to the answer, for example, and that's very natural. And what we need to do is like two things. First of all, focus on what they want us to find. So let's highlight that. So that's this length here. And angle BFC is going to be where we go from B to F to C. So it's going to be, if we go straight, okay, that was a strange line. If we go straight from B to F and then to C, we'll create an angle here. And as you can see, this is on this diagonal sort of slanted surface. But at the end of the day, it's just a right triangle. And you can draw it off to the side, like so. Where that's F and that's B and that's C. And right triangles we can do something with. And it's most likely if we're going to be finding the angle, we have to have two sides. That's how trig works. The trig ratio for one example, let's say it was tan, is opposite over adjacent. We need two of them to find the remainder. So since the unknown is definitely the angle here, we're going to need two sides, and we've got one already. That's down the bottom. That's 10 meters. Would it be really nice to have this one? I feel like this one is a good one to have. Like B to F would be difficult. B to F is linked to the triangle, which is BEF, and then that would require the similar sort of approach that we have here, but we have less information. We at least have the 10 in the bottom one. So here comes my second point. Obviously we looked at where they want, and you can highlight that. The second point is, where is most of the information? This is the best place to start a question, especially the geometry questions, because they're often made up of multiple shapes sort of pinned together, even if this is 2D or 3D. And one of those shapes will have more information than the others, and that's where we can start. And eventually cascades into where we need to be rather than where we can start. So hopefully you can see that most of our information is here in this triangle. Now it's drawn in 3D there, but we're going to draw it again. So triangle ABC looks like this. Yeah, that's not good enough, is it? Let's draw it like that. So here's lots of information. And then 5. All right, so this is a non-right angle triangle. And if we split it down the middle, there's no way of telling if that's the midpoint. There's nothing here to say that in fact, there's evidence to say that it isn't, because one's 50 degrees, one's 40. So it's a bit off center. If we drew that line down, we'd be guessing about where it ended up. So this is definitely a non-right triangle. Therefore, we have two options for that. So sine rule or the cosine rule. So it's definitely not going to be trigonometry with the ratios. It's going to be a more advanced method. Now, how do we know which one to do? Well, cosine is going to involve all the sides. This does not. It only has one side. So I'm going to try sine rule first. Definitely the easier one out of the two. Sine rule is predicated on a relationship with pairs of angles in their opposite side. I would not use a formula. I'm sorry to say, I'm not going to give you too much bad practice, but I wouldn't use a formula here. I would use the idea of pairs and ratios. But let's, before we start this, consider that we wanted this side here. So we'll call that x, and let's call that a side that's involved. So this is what I mean by pairs. You've got an angle, and then you've got its opposite side there. There's one pair. And we have, well, there's an angle, but we don't have its opposite side, do we? But this is definitely a side. Can we do something about knowing the angle up there? Yes, because 50, look at that, don't write in highlighter, 50 plus 40 is 90, which makes that a very interesting angle up there. That's actually a right angle. So little did we know, we actually have a right triangle here. What does this mean? Does this mean we have to use sine rule? No. In fact, the sine rule is going to be interesting, because if we put this in the sine rule, sine of 90 equals 1. So we're going to end up getting rid of it, and it's going to turn into a trigonometric ratio. So despite the fact we thought it wasn't a right triangle, it turns out that it is. Let's see what happens with the sine rule to show that we can't really go wrong, and put it in. So the sine rule says x over its opposite angle, sine 50, is equal to the 5, and that's the other pair, over sine 90. And we know that sine 90 is equal to 1. So this whole side is equal to 5. And then we will find that x is equal to 5 sine 50. So bear that in mind for a second while we get rid of this need for a sine rule and treat this like a right triangle. And we'll use the 50 as a focus. Okay, so this is our focus angle, because we could have used a 40, but we're going to use the 50. Now, the hypotenuse is the 5. We have to use that because we've got it. And the x is the opposite. So we've got hypotenuse and opposite. That's sine rule. Sine rule says sine 50 is equal to the opposite, which we don't know, over the hypotenuse. If we rearrange that, hey presto, there's actually a 5. Let's differentiate a bit better. 5 sine 50, we get the same thing. Look. And so it, the sine rule will turn into the normal ratio in the case that we have a right triangle and we didn't know it. Well, we did know it in this case. We figured that out fairly sharpish. Let's continue. I'll get rid of all of this because that was, do we want to say it was unnecessary? No, it was part of our journey. I will write the 5 a bit better. Now we just have to put this in a calculator and we'll put it over here with this bunch. Make sure it's in degree mode, of course. 5 times sine 50. And we have 3.830222216. I'm going to leave it in my calculator because I'm pretty sure this is going to be part of the next calculation. We can now update our diagram. I'm going to call it 3.83 ... because it's not the whole thing. Now, if we wanted this angle, we just have to use a different ratio. So in this case, this is the opposite. And this is the adjacent. Oh, I didn't know that, but it is tan after all. So tan of the unknown theta is equal to the opposite, which is our 3.83 ... all over the adjacent, which is 10. Okay, so now we've got that number 3.83, etc. in the calculator. We'll divide it by 10 straight away, and we get 0.383. So tan theta equals 0.383, etc. And what we want to do to get rid of this tan, because currently this is tan theta. We just want theta, meaning we need to get rid of tan. In between tan and theta, most people I teach think that there is a multiply there. It's not the case. To get rid of tan, we need to apply tan to the -1 to both sides, like that. In effect, what happens is this will inverse itself, so it no longer functions. It just has no effect because it's been inverted. This will do the opposite, and therefore it becomes just theta. And in our calculator, we press Shift tan to get inverse tan. We're going to click the button answer because we kept that on our calculator, and we get 20.957. And we have not rounded until this point, and it's the final answer for both. Yeah, it's actually a final answer for both because there's no more work to be done. So we're going to round it to 20.96. Does it say how much we need to round it to? No, but we'll round it here to 20.96 because otherwise it's a difficult rounding job and it becomes too rounded. And this is degrees to 2 decimal places. And we no longer need for this full on the length x, which is in fact what we were asked to find BC. So we're going to call it BC. In fact, should we call that angle what we were after? Angle BFC. So we'll call it BFC like that. And BC will be 3.8 meters to 1 decimal place. Lovely job. I'm sure you got that correct. And that's the end of the trigonometry basics. So if we have a quick brief look at where we started. We started with the trigonometry of compound shapes, so we had to work our way from one to the other. We had a bit of trigonometry as well. In fact, that was all trigonometry. Was it all trigonometry? Yeah, there was some Pythagoras here. There was some cosine rule. Sure we did Pythagoras, did we? In fact, that was way further back. It was here. So here's Pythagoras for 2D and 3D. And then we've got trigonometry in 2D, and then finally trig in 3D. And you'll see there's no difference between trig in 3D and 2D, except you just have to find where that shape is and draw it separately in 2D. Okay, moving on to probability, my favorite. I feel the world needs to do more of this. So don't be shy of trigonometry, of probability. The two major things are going to be Venn diagrams and tree diagrams. The major concepts here are independent and dependent events, and there's a little bit of notation. So let's go on with some question. The probability of Bob winning at the tombola is 0.1. Independently, the probability that he wins on the coconut shy is 0.15. By drawing a tree diagram, find the probability he wins bundle. Okay, so don't worry about the question yet. It says by drawing a tree diagram, that's where we're going to begin. Tree diagrams look like this, if you didn't remember. And this first section is event number 1, so that's going to be the tombola. And then this is going to be the coconut shy. Why is there two branch sets for the second event? That's because there has to be 2 options for this first event, and then for the second option on the first event there has to be another 2 options. Okay, because despite what happens in this first event, whether it's win or fail, you're going to go on and still have the same 2 options for the second event, so you have to map all of that out. Do we want it to look that ugly? Maybe it doesn't matter too much. Right, so my tip to you is to do the first one fairly wide. Give yourself some space. So tombola winning, I'm going to call it win. And doesn't mention winning, the opposite of winning. So we're going to say, we could call it, this is really technical, not winning. And that might be the best way of doing it. But I feel like it's much easier to see a different letter. So we're going to say win, lose. If he wins at the first one, which is tombola, and we're going to put this here to remind ourselves, then you can still win or lose. Why do I think fail is a better letter? I'm going to go with L still. At the second event, which is the coconut shy, the sea shy. Space, perfect space, eh? These do require quite a bit of space. Okay, so these are the, there's a couple of ways of doing it. You could have written these on the sort of branch, but I don't. I tend to put the numbers on the branch. So the probability of winning at the tombola is 0.1, and all of the probabilities in one event have to add up to 1. So there are 3 sections here that need to add up to 1. That's these two, and these two. Okay, so if we know 1, we know the other because it has to add up to 1, right? So this must be 0.9, like so. And with the coconut shy, it says independently. That means that it's not affected by what happened before. So if he wins on the tombola, that's not going to make him any better at winning the coconut shy. Or if he loses at the tombola, he's not going to be depressed and do worse on the other one. It's independent. The probability he wins on is 0.15. Okay, so that's going to be the same in both of these situations, 0.15. And if that's the case, 0.85 to lose, because that has to add up to 1. That's the golden rule in the statistics world. By drawing a tree diagram, we've done it. We need to now find the probability he wins one or both events. My recommendation for tree diagrams, seriously, write your outcomes right now. Before you've even read the question and what you have to do, trace along the branch. So like this, trace along the branch and think about each of the possible outcomes and write down WW. That was win-win. This one was a win, then lose. This one was a loss and then a win. And then this one is a loss. Okay, the probability that he wins one or both events, which is that? Well, one or both. So in the cases where he wins one, it's here and here. That's exactly one win. This one, there's no, down at the bottom, it's loss. That's no good. So that's exactly one. And then both is this one. So we're looking to find the probability of all of these. Now, there's a little bit of language around probability that you have to be fully aware of. When we see the word and when you want more things to happen, the probabilities are going to get multiplied together, because more things you want happening is less likely that you're going to get them. And if the word or is used, or in any context it feels like an option, then we're going to add those probabilities, because if we are given the more chances to get a win, then we're going to add the probabilities, because we should be more likely to win because we get given more space. The best way of visualizing this, I think, is a dartboard. Let's say you're going to throw a dart at the board. What do darts look like? Nothing like that, right? You're going to throw a dart at the board and it was split into 8. And if you get it in this region, then you win. So as you can see, there's a 1 in 8 chance of winning there. But if you suddenly said that you can win by this or this or this or this, what's going to happen to your chances? It's not like you're replacing the place. You're actually increasing the amount of surfaces that give you a win. So that should increase your chances. If you can win with, let's change color, with this, which is 1/8, or this, which is 1/8 of the space, or this, or this, what's going to happen to your probability? You're going to add all those together, so it's 4/8. And that's much bigger than just the 1/8 before. So chances increase when you use the word or. Okay, so that's your lowdown on the and or process. Let's take a look at this. In the first scenario, win-win, we want the tombola and the coconut shy. We see and is a multiply, so that's going to be 0.1 times 0.15. And you can go ahead and actually do that. It's probably easier as a fraction. By the way, if you don't have access to a calculator, you can, right, this is 15 over 100. And you can multiply those together like that and do it in fractions. There's nothing wrong with that. But I do have a calculator, so I'm going to work that out as a decimal. And that's 0.015. Decimals are not always the best. We'll just work with it. Now, the second scenario is a win-loss, and you want a win on the first and a loss on the second. So again, we're going to be multiplying across. There's a general rule for you. When you're going across from left to right on these tree diagrams, we're going to be multiplying. Yes, we are. And that gives us 0.0. That's a shocker, isn't it? I didn't need a calculator for that. I should have just done it. Right, 0.9 times 0.15. We can find 10% and take it off, or we're just going to put it in a calculator. There, 0.135. There we go. Okay, so those are the three scenarios that give us a win. It could be this, or this, or this, in which we will win. And as you can appreciate, when we're using the word or, we add them together. So to find the probability that, you see there's the word or there, that he wins one or both events, it's going to be 0.135. So we can say probability of one or both. That's probability notation, yeah? That P outside means probability, and this describes probability of what? We'll add them all up. 0.35 plus 0.085. La-di-da. And 0.015. Anomaly. Did I get that right? Yes. I think I've done them all now. It's 0.235. Wow. It's an important number to me. Not anymore, but when I was a kid, that was the last 3 digits of my phone number. Many moons ago. Doesn't mean anything now. Trust me, I don't use it in any of my passwords, so don't even go thinking. All right, so we've got a probability that he wins one or both events. Done, in the bag. The tree diagram alone is typically worth 3 marks. So to then go on and do something like this may give you another 2 or 3. So that's really good jobs. The next one, the probability that he wins neither. So that means that he doesn't win, okay, in both cases. Neither means none, right? So that if he wins neither, that means it's loss. So we just need to go for that last little thing. Now there's one way of doing this, which is 0.9 times 0.85. And it'd be a really good exercise to see what that is and then show you a different way of doing it. So this turns out to be 0.765. Do you, does that look like an interesting number? So winning neither is loss and loss. That's why we did the multiply. That is an interesting number, right? Because these two numbers added together are going to give us 1. Now, you remember I said earlier that there's certain things that add up to 1. That's these two probabilities, these two and these two. But also, at the very end, this is our probability space. All of these numbers will also have to add up to 1. So if we know 3 of them, because we just found this was 0.235, then we can just simply do 1, because they all add up to 1. 1 take away 0.235, and that will give us our 0.765. Okay, so a couple of ways of doing that one. Tree diagram is really nice. Got the structure to work through, and the rules are very similar every time. Okay, know how to draw it out. Get into the habit of writing these bracket things at the end. These are our outcomes for each branch, and just make it an automatic habit of even multiplying across to get these numbers. And then the questions are so easy. It's just which ones you're going to add together. Okay, let's get to the top of this. A tin of biscuits contains 10 chocolate, 5 toffee, and 5 white chocolate flavors. Kate chooses a biscuit at random and eats it. Oh, of course she does. She then chooses another biscuit randomly. By drawing a tree diagram, find the probability that... so what did she do, that Kate? She ate the biscuit, but in doing so, turned this question into a dependent question. So, oh, hello, Chris Shiv Sharma. 0.235. Were you guessing before I wrote 0.235? Because if you were, well done. We got the same answer. Maybe you could let me know. So a tin of biscuits contains this. What was I saying? That Kate chooses a biscuit at random. She suddenly turned this question into a dependent event. It means that she's changed the biscuit tin forever. She's taken away one of the biscuits and the balance will never be the same. It sounds like Star Wars in a biscuit tin. So a biscuit tin has these sort of things. Let's draw a tree diagram. So you have 3 options now. So the tree diagram is going to look a wee bit different. So you've got 1. I'm going to actually make it a lot wider because, well, you can only make it as wide as you have space. This is what I've learned. The first one might be better to be wide. So we've got chocolate, toffee, and white chocolate. We're gonna call that CTW. Chocolate, toffee, and white chocolate. And it looks as though if she did eat whatever the biscuit was, if she ate it, there still will be some biscuits of each flavor, and so each of these are going to have 3 coming off, like so. So we have to be respectful of the space of the other branches. And that's not too bad, is it? That's not too bad. Now, each of these are going to have CTW. The chances, if she takes a second biscuit, that she could have 2 of the same. So yeah, she's picked 2, and now we're drawing the diagram. We have to fill in the probabilities now. The probabilities are not given like in the last one. They are implied by the question. Okay, so in the first case, how many are there in total? Well, there's 20, and 10 of them are chocolate. So this is going to be the 10 over 20 branch. 5 are toffee. This is the 5 over 20 branch. And 5 are white chocolate, so 5 over 20. This is where it gets a little bit sticky. By any chance, could you do differentiation? Yeah, I mean, I can do differentiation for sure. I have got a ton of videos on differentiation. I did a whole series on TikTok, and I do it with my method, which, well, I don't really need a formula. You don't need to memorize or use a substitution. It's kind of intuitive and really fast. If you're looking for all the different methods, or you're just looking for basic differentiation. This is essentially my GCSE help pack, which takes us through all the questions for GCSE. Differentiation is not going to come until further maths, GCSE or A level. So let me know what sort of level you want, and I could stick around if I've got the time. Right, C. So in the second time, this is where things have changed. There's 1 less biscuit in the tin. So that's going to be 19 in the biscuit tin. And since the first one was a chocolate here, that means that there's 1 less chocolate overall. So instead of there being 10, there's now 9. You see, you have to think about this a little bit. But one good thing is for sure, you get a mark for writing 19, by the way. So if you recognize that the overall total went down by 1 and it's evidenced, you straight away got yourself a mark for recognizing conditional probability. The biscuit tin, it changed forever. And you recognized that. Okay, so all of them are 19 because there's one less. Question is, have the flavors gone down? Well, because the first one in the top 3, so we're talking about this section here, the first one was chocolate. So the others remain at 5. Okay, so that's if we went down the chocolate for the first. If the first one taken was a toffee in the middle, that means chocolate remained untouched, but toffee's gone down to 4, and white chocolate remained untouched. And the same for the last one. We still have 10. If the white chocolate was first, we'll still have 5 toffee, but the white chocolate will have gone down to 4. Okay, we've got some lovely fractions here. And we're going to, in what I recommended was put the outcomes CC, CT, CW, TC, TT, timetable, TW, thanks when. I just sometimes have a habit of saying the first 2 words that come to mind. Whence came, when Tarzan, and I don't even know. What win? I don't know why I'm saying what win. What a stupid thing. Anyway, let's carry on. We've got these outcomes and we're interested in the 2 white chocolate flavors. Okay, so what is the probability of that? Well, we look for the only option that we can, which is this. Now remember, this means white and white. So and implies a multiplication. So I'm going to double check whether it chooses 2 white. Yeah, that's right. When it says chooses 2, it's kind of strange, as if she could see, but actually this is quite important that they're chosen at random. Yeah, so it says randomly. But yeah, let's just make that point. This is 5 over 20 times 4 over 19. And that's going to be, well, should we keep it as a fraction this time? Because like that is a legitimate thing, and fractions can be quite nice. So that works out to be 1 over 19. And that's actually, in fact, the answer to our first question. 1 over 19. Okay, she didn't get a toffee flavor. What an interesting question. If she didn't get a toffee flavor, we're looking for all of them that didn't have a T. So this is a chance to get through and do some multiplication. So I'm going to go through and do all that now, because that's going to take some time. We don't necessarily, when we've got all of these, we don't necessarily need to do all of the multiplications, right? Because it might mean that we can save ourselves some time. This is off bounds. So is this, so is this, so is this, and this. So thankfully we've already got 1, and now we've got a second, and let's get some more. So 10 over 20 times 5 over 19. That's 5 over 38. And one last one, that's 5 over 20. It makes a big difference when you use a nice calculator, because they've got the fraction button and the interface is so nice. All right, so actually I should have recognized that we've got the same multiplication there. There's just the 10 and the 5 switched, right? Anyway, so we've got all of those. And remember, she didn't get a toffee is in this or this or this or this. So we need to add all those together. We've got 5 over 38 times 2, which is 10 over 38. So that can save a bit of input, plus 9 over 38, which you could just add as 19 over 38. But I'm putting it in anyway. Maybe I think to myself, I doubt myself. You can multiply this by 2 and it would be over 38. So in fact, there's much less need for a calculator than all of that. 1, 2, 3, 4. Okay, so I think we're there. The total for not getting toffee flavor would be all the ones where T wasn't present, and that's 21 over 38. And finally, the probability of getting strawberry. So the probability of getting strawberry flavor, what? Yeah, no, I had to double check there. Sometimes they'll get you. There is no strawberry at all, so you're going to just write 0. Sometimes it is 0. Be brave. Don't think the question's wrong. It's impossible to get strawberry if there's no strawberry there. Okay, we've got a few more questions. That means we're probably going to wrap this up in about 15 minutes. So if you're looking for basic differentiation, not a problem. I'll just grab some of those questions out in about 15 minutes and we can do some for 10-15 minutes. If you've got any more information you want to give me about the differentiation, as in where are you on? Like, are you differentiating polynomials? Are you differentiating like logarithms, exponentials? What do you want? All right, so there are 25 customers at an Aston Martin dealership. There are 16 who have a DB7, good old DB7. 14 have a Vanquish, and 6 that have both. Let F equal DB7 and G equal Vanquish. Ah, well, it's very controlling. Draw a Venn diagram to represent this information. Okay, so Venn diagrams always have a space in which they're operating. And thanks to the wonders of my tablet, I can just make life easy. Now, there are 2 categories here, right? I think, yeah. So then therefore we can keep it at 2 circles. 2 circles overlap like this, and then the third one is going to go in after you've done 2. So always start with 2 either way. DB7 is F and Vanquish is G. Nice. 25 customers in Aston Martin dealership. So those are the total. There are 16 who have a DB7, and the DB7 is F. So there's 16 in this circle here, and 14 have a Vanquish, and 14 in this here. 6 have both. Lucky devils. Been around for a while. So if that's 16, that represents 10. If that's 14, that represents 8, right? Because the total in those circles have to be 16 and 14. Therefore, we've used a bit of logic to figure that out. But now there's a bit missing, perhaps, because there's 25 customers. So what does this add up to? 16, 24. So the last one goes on the outside, and this customer doesn't have any. So maybe they totaled it, or maybe they're about to buy. Who knows? But they are a customer of what? We don't know. If a customer is chosen at random, that's the key point. They have to be chosen randomly. Then the probability of F. Well, this is a frequency Venn diagram, right? So we need to know that total. We'll keep it in mind, 25. For the probability of F, we just need to find the total in F, and that makes up our question. So this is the circle of F. You can see that adds up to 16. And so this is going to be 16 out of 25. The probability of F and G. So this N means intersection. Now, I like to do my intersection and everything really with a tally. And I've got a video out on the tally method, and it goes something like this. So if we want F is this and this. Those are the 2 sections pertaining to F. G is this and this. Looks like they share a section. An intersection, it means where they appear twice, where they overlap. Okay, so in that sense, hopefully we can see that that is this center point here. All right, so that's the point that we're talking about for this question. So that is highlighted 6 out of 25 for us. Okay, this same this same tally method is going to be really useful when it gets complicated, like with these next 2. So we're going to take not F. So if the 10 and the 6 are F, not F is outside of that circle. So it's here and here. Don't forget the outside bit with a 1 in it. And then G is, again, we've done G, it's here and here. And intersection is the bit where they appear twice. Hopefully you can see that this means it's the crescent moon, the half moon, or whatever you want to call it, because that's where there are 2 tallies. All right, so what does that tell us? It means that 8 is the number of people we're interested in here. So it's 8 out of 25. And then the last one, This little dash, this little line there, prime sometimes, it means not. So if we found F union G, then the not means that it's the complement, like we're going to take it away from 1. Let's see how that pans out. First of all, let's try and identify the region F union G. So union is the other way around, and it's all sections with a tally. And you'll see what I mean because we're going to do the tally method. So F is, well, let's get clear this first. F is here and G is here. And the union speaks on all of the parts that have a tally in. So that is that and this. So this is in fact the union of F and G. It's very famous. It's everything. It's A, F and G and both. And what we're looking for actually is the complement of that, because in fact we don't want that. We want everything that isn't. And as you can see, the only thing that it isn't is the number 1 on the outside. So that's going to be 1 over 25. Okay, so there's Venn diagrams for you, and the fabulous tally method is fantastic. It works for very complicated ones, and it makes your life in the exam very easy. You don't need to guess stuff. You've got a reliable method that can really help you. So go check out my video on the fabulous tally method. That's up on my channel right now. And let's go to the last question. All right, so as you can see here, we've got some definitions. I'm not going to get rid of those. They could be useful. So let's move it up as much as we can. Okay, so after we've drawn this, it looks like there are some more follow-up questions. To see what this notation means in words, see below. Oh, okay. No, that's not follow-up note. Oh, that's brilliant. We finished. Hooray! That's really what you need to know. There's a notation here. This is what it is. Take a look down here on your document. Probability of F. This is the obviously statistical speaking stuff, and it really saves you a lot of writing. Look how much writing it is. What's the probability that a random customer has a DB7? So much easier, right? So you can see one reason that they use this notation. But if you really wanted to understand, I gave this key for you so you can see what it meant. Okay, so the last set of pages here is simply a planner that you can use for, I mean, there's not much time left. I've had this up here for a couple of months now. But if you wanted to use a planner for the next few weeks for your revision, it might or might not be useful to you, but I think that it's nice if it's there. Yeah, answers are going to be here. And there you have it. All right, so we've got to the end of the questions. Thanks, everyone. And what we're going to do now is answer a few bonus questions for people that have turned up. This is definitely not GCSE by the sounds of it. Oh, I think I've added too many pages. This will do. So in this little space, I will go through the basics of the differentiation as requested. I haven't heard, Chris Shiv Sharma, I haven't heard much from you about what you wanted to do. I can easily do differentiation, but without the input, I'll probably end the live stream to keep it GCSE only. Happy to go live again at another point. I mean, when do you need it by? I guess you weren't listening earlier when I asked the question, but that's cool. You know, you're not expected to be there. all the time. I'll ask it one more time. What type of differentiation do you want to do? Do you want to do the polynomial or trigonometric functions or chain rule or what? I feel like the chain rule is just the best. I don't mind waiting a bit. I can wait and then just cut it off at the end. I can edit the video if nothing happens. So it's cool. I got some time to wait. Still there? Okay, well, I'm not hearing back from you, so the ultra basics are going to be just like how to do it. So let's say a function is 6x. There's a couple of ways of writing this. It could be y equals 6x, or it could be a function of x equals 6x. And if you want to differentiate it, the first derivative in this case can be written as f dashed of x, or if you're using this notation, the derivative of y with respect to x would be called dy over dx. Okay, so there's two ways. It's absolutely the same. One is different form, like notation. And essentially, we're going to put this up here as to the power 1, because that's what it is. To differentiate, all that happens is that we bring the current, actually, should I do 6x? I meant to write x to the 6, because it's going to be a bit of a naff differentiation. All right, so what we do is we bring the current power, current index, which is this, down the front, multiplying it here, and we take away 1 from the power, so that becomes 5. And it doesn't matter if you use this notation, you're going to get the same answer. So that's how we find the derivative of a very basic function. And if you had x to the n, the general would be that the n came down the front, and then you take away 1 from the power. That was f of x going to f dashed of x. Okay, so that's a generalization if you want it. This works with a number of them. Let's say we had f of x equals x to the negative 2, then f dashed of x equals negative 2, because that comes down the front, and we take away another one from the index and it becomes negative 3. Very simple. So how would we do it if it was x squared times x cubed? Well, the first thing is to simplify what we have. Okay, so that's f of x, and therefore f dashed of x is much better handled when we have a single term like this. In fact, probably the only way to do it. Simplify first. It introduced the idea that you want to simplify first. So f dashed of x is going to be taking that 5 down and turning the index to a 4. And it's the same with anything. Simplify first. Okay, so let's get a bit more complicated in terms of simplify first. What if it was f of x equals the square root of 36x cubed? Well, they can't really apply that rule, can you? You can't. This doesn't make too much sense here until you get it into a proper index form. So I think the first thing to realize is that the square root is the power half, like this. And then since these two are multiplied together, we can apply that half to both of them. And this is x, and that's 3 over 2, like so. And then 36 to the half is 6x 3 over 2. Now, this is a very interesting point because it's the first time we see a number in front of there. Now, you can later prove this using the product rule. If this was 6 times x to the 3 over 2, and you took this function to be u and this function to be v, you would therefore use the product rule. And you'll see that this 6 will just disappear because it's a number. The derivative goes to nothing. And so you would end up ignoring it. And that's essentially what you do. You just ignore this 6 here. It has no effect on what you're going to do to this, except when this power goes down, you will multiply it together. So if you want to find f dashed of x, we're going to put the 3 over 2 down the front, multiplying the 6, and we're going to take away 1 from 3 over 2. Now 3 over 2 is 1.5, and so if you take away 1 from that, you end up with a half. Another way of looking at that is 3 over 2, take away 1, would be taking away 2 halves. And therefore you're left with 1 half. Okay, so tidy it up. 6 times 3 is 18 over 2, which is 9x to the half. And sometimes you don't want it in that format to substitute. So you can write that again as 9 root x. Or interestingly, if you're interested in something else, in fact, would that work? Yeah, that would. So this is a root x, and then 9 is the square root of 81. So you could write it as 81x. I don't know what floats your boat. It really depends on what you're after for the question, but this is absolutely good enough for the derivative. I don't know how much more you want me to keep going on these. What about differentiating polynomials, I guess? So we've done 1. So what if the function instead was 4x squared, I don't know, take away 3x plus 5. And in this case, we just differentiate term by term. So we start with this one, and we get 8x, and the 2 turns to a 1, but we don't need to write the 1. The 3x, this one is just going to become minus 3. How does that work? Well, if you've got to the power 1, this 1 is going to come down the front. So it's 1 times negative 3. And then the x, you're going to have, like, take away a power, is going to be x to 0. Anything to the power of 0 is 1. And so we end up with negative 3. This is the case all the time. As you can appreciate, if there is a power 1, it's going to get rid of itself. So you only end up with their coefficient. So it's quite nice and neat. So you just write minus 3, and numbers disappear. Oh, how does that work? Well, you notice that this is a squared, this is a power 1, and this must be therefore power 0. Well, it is. This is equal to 1. And so what happens when you, let's do it at the side, what happens when you differentiate a term which is x to the power 0? The 0 goes down the front. 0 times 5 is 0. Now, you could argue then that that's 0 times x to the minus 1. Well, there's something, but it's times 0, so it goes to nothing. So numbers disappear. And that's the problem. When you differentiate, you lose information. If I differentiated it, and I got to this, if I wanted to go backwards, how could I tell that it was a 5? There's nothing in here in that blank space that indicates that it was a 5. So when you're looking at integration, the antiderivative, that's one of the problems. That's like when we're going backwards, all of this works backwards. You could say that this one here, for example, we can add 1 to the power, which is 2, and then we can divide by that new power, so we get 4. Okay, we can go backwards. With a 3, we can just add an x. Essentially, you're adding 1 to the power, which is now x to the 0 goes to x to the 1. The 1 gets divided into the -3, it stays the same. But this last one, absolutely unknown. And that's why for general integration, we plus a c to indicate that there's a number possibly that could be there. Sometimes c is 0, but that's part of it. So that's how polynomials get differentiated. And that just continues. I suppose, should we look at one where we might have to actually do something with? So f of x, let's say the polynomial is 4x squared, take away 8x plus 3, and you're going to differentiate this. So we're going to get 8x minus 8. What do we do with this? Why do we differentiate? Well, this up here, as you can appreciate, is a quadratic. Okay, it looks like that, whatever. When we differentiate it, it turns into a straight line. And this straight line represents the gradient of the quadratic at any point. So let's just draw that again. If I was to pick a point like here and draw a tangent to it, then the gradient of this line can be found by picking 2 points and doing the difference in y divided by the difference in x, and you can find the gradient of that curve at a particular point. What's brilliant is that this function here will do that for any given point that you want. So, for example, we want to find the gradient of this function when x equals 4. Okay, so we want to know how steep that quadratic is when x equals 4. Then we would put 4 into the gradient function, into here. How do we tell everyone that we're doing that? We replace the x with the 4 that we want to put in. Okay, so x is now 4, and that would be the same on the right hand side. X has to be 4. So we end up with 32, take away 8, which is 24. That's quite a big gradient. But when x equals 4, the gradient f dashed of x equals 24. And that's really steep, isn't it? It's like that. But that's how it works. You can substitute a value of x into the gradient function and find the steepness at that point. That's the purpose of differentiation, for one simple purpose anyway. What else would we look at? Oh, that's a pretty good skill. I'll probably keep going for 5 more minutes, unless someone speaks about this and says, yeah, keep going. So if f of x equals 1 over 4 root x. This is a great lesson. You need to be able to do this. It's a great lesson in why you need to know about your surds and your indices, because this currently you can't really differentiate nicely. You need to turn this into index form. You might have some ideas on how to do that, but essentially the 1 over, meaning a reciprocal, that means like to the -1. There's a couple of ways of thinking about this. I'm going to write it as a quarter multiplied by 1 over root x. Just take a moment to look at the two expressions, the one on top and the one below, and see that they are equivalent. Now, I'd say this a lot, but maths is about finding the equivalent forms in order to illuminate some new truths. So if we can write this in this way, it makes life a bit easier. So now this 1/4 is going to be multiplied by, we're going to deal with this reciprocal, okay? So the 1/, actually means reciprocal, which means the power of -1. So I'm going to write this as 1/x to the half. And then what effect is this 1/, going to have? It's going to turn that half negative. And we've finally found the index form. This is something we can differentiate. Okay, so now if we're told to find the derivative, we can totally do this. So we're going to be multiplying by -1/2 down the front and keeping that 1/4 and times by x to the -1/2. Nope, we're going to take away 2/2. So it's going to be -3/2. And I feel like this is a bit of a tricky point for people. Like when you've got like fractions and you have to take away 1. So one of the powers could be 1/3 and you have to take away 1. Well, that's going to go to -2/3. You have to have a good visual in your head on how to take away 1 from fractions. And we tidy up, okay, so -1/8 x to the -3/2. And that's the derivative. So tidy it up first, get it in polynomial form, and then you can go for it. Got a couple more minutes, haven't we? F of x equals, I don't know, what do we think? Maybe we've got a separate one on top and on the bottom, x squared. Again, you're getting the gist of this. You have to get it in polynomial form. You have to divide it. Hopefully you know that this can be written as 2 separate fractions that share a common denominator. And then how do we deal with this first one? Well, it's kind of a couple of ways of dealing with it, but the way that I would deal with it is to turn it to 1/x. I would cancel one of the x's first. And this side is really awesome. I would do it as 2 times 1/x squared. So I want to get this sort of 1/, and in all the cases, and then I'm happy we've got my coefficients out there. Why is that useful? Well, you can replay this as much as you want, but it's useful because these reciprocal forms are fairly well known. So 1/x, it can be written as x to the -1. Then we're going to take away 2 lots of x. Now remember this 1/, business, it turns the index down here to a negative. So that's going to be -2, like this. Now we've got it in this form, we can actually differentiate it. So that was f of x, f dashed of x. We take the minus down the front and we take away another one. Here we're going to take the -2 down the front, so that's going to become +4. And we take away 1 from the index. Now this is not always the best form to leave it in. We're going to sort of turn it back into fraction form. I've actually run out of space, so I'm going to continue. Don't do that. I'm going to continue up here. So how would we do this? Well, we've got -1/x squared would be turning that next one back. How did I know that? Well, essentially, this negative out the front means that the whole thing's being multiplied by -1, and separate issue is x to the -2. I know that I can replace the negative here with 1/. So -1 times 1/, whatever's left. That was an x and a squared. So that's how I get to that. And then now I've got a -1. Typically that will come in to the top there. So maybe I could leave it up the top, but I know that since there's only one of them, I can just put it out the front and it's a bit neater. All right, mini lesson over. With the second one, this is 4 times x to the minus 3. Now let's deal with this one first. This negative power is going to straight away go to 1 over, and whatever's left is going to go underneath. That's x cubed. Now when you're multiplying a number by a fraction, it always multiplies the top. That's different from a negative. A negative is -1 and therefore has no effect. It doesn't matter where it goes. But with a 4, it has to go on the top. So the final over here is going to be 4 over x cubed. Why would you have it in one form or the other? Well, essentially, one form is better for substitution. That's the fraction form. That's better for working it through. And the other form, polynomial, the exponential form, is better for the actual differentiation. We can go a step further here if we switch these around. So essentially we want to match the denominators. So that's going to be x over x cubed. If we multiply the top and the bottom by x, and x cubed there. So now we can just take away the top. Why do I say take away? I know it's in the wrong order, but we can switch it round. It's a positive 4 over x cubed. Take away a negative, or sorry, add a negative x cubed. And with a common denominator, we have 4 minus x all over a single x cubed. That's the neat finish that we were looking for. All right, we're going overboard, I would say, and I don't think Chris Shiv Sharma is here anymore. So anyone that's still around and looking at this who came for a GCSE, hello, this is year 1 pure AS level. Sometimes they call it AS level instead of year 1 maths. Okay, so might also call it year 12, and it's under the topic of calculus. So call it a preview of what's coming. I do calculus all day. It's many people's favorite subject. But yeah, time to get off of here. We came to do what we wanted to do. We've done the GCSE. Those are the questions that are going to give you amazing grades. Anything else on top of that is a bonus. So best of luck, and I'll see you on Saturday for the Saturday morning tonic. And it's not long till the exam now. So let's get going, everyone, especially if you haven't already.